Alright, so we're going to try a waves question. This is called the whirling buzzer. So the speed of sound in air is given as 3.43 times 10 to the 2 meters per second. And James attaches the buzzer to the end of a piece of string, and he whirls the buzzer above his head in a horizontal circle of radius 1.02 meters at a constant speed of 16 meters per second. And we're given here a little picture of James and Sabina. Describe the motion of the buzzer when Sabina receives sound waves with the shortest wavelength. So describe means we don't really have to give any explanation. So she's going to hear the shortest wavelength. She's going to receive the shortest wavelength sound when the buzzer is moving directly towards her. So we can just say the buzzer is moving directly towards her. And we know that's because they bunch up, and therefore we get a shorter wavelength in front. But we don't need to say that because it was just a describe question. If the frequency emitted by the buzzer is 512 Hz, show that the lowest frequency heard by Sabina is 489 Hz. Okay, so this is due to the Doppler effect, so we're going to use the Doppler equation. We have the observed frequency is equal to the original frequency times VW over VW, and this is going to be a lower frequency because it's which means we're going to be adding Vs here. Okay, and then we'll substitute in our numbers. F is the original frequency, which is 512. And then VW was 3.43 times 10 to the 2. And we're going to divide that by 3.43 times 10 to the 2. And the lowest is when, at the moment in the circular motion, when the buzzer is traveling directly away from Sabina. In other words, it's got the same speed as the buzzer, but it's directly away. So the source speed at this stage is going to be 16, which was the buzzer speed. Okay, and then we're going to substitute these numbers in here. So we have 512 times, and then bracket. And on the top we had the wave speed, which was 3.43 times 10 to the 2, which is 343. And we'll divide that by bracket 343 plus 16. And we get 489.18. Which is about 489 as we wanted. Okay. Sabina stands a very long way away from James and listens to the buzzer. The sound appears to be increasing in frequency as the buzzer travels from point C, that's here, to point A. Explain why Sabina hears an increasing frequency between point C and point A. So at point C, we're hearing approximately the lowest possible frequency. As it heads towards D, it's going to increase, and here the velocity is this way, so it is the true frequency. And then at point A, it's going to be approaching Sabina, so it's going to be Doppler shifted up. So we're going to start off with it Doppler shifted down, moving away from Sabina, and then we're going to end up with no approach velocity, so the true frequency at D, and then the Doppler shifted up frequency at A. Okay, so let's write each of those things. So we can say at C, source is receding. That means moving away. So wavelength observed is longer. Wave speed is constant. So frequency is low. At D, the source is neither receding or approaching so Sabina hears true frequency, i.e. 512 hertz, as we said. The frequency here was about 489. And then we can say at A, source is now approaching. So lambda is shorter, and as V is constant, F will be higher. So we can say, maybe I'll write in the equations next to here. So here we had F is equal to F dash VW over VW plus Vs. Here we say F is equal to, it should be the other way around, F. And then here we can say F dash is equal to F. And here we can say F dash is equal to F VW over VW minus Vs. Okay, so that kind of explains why the frequency is getting higher and higher as it moves from C to A. James wants Sabina to hear beats. He puts a second buzzer, which is also emitting a sound of frequency 512, on the ground. James again whirls the original buzzer above his head, but at a different speed. When the buzzer is at point A, James lets go of it, so the buzzer flies towards Sabina. Sabina hears a 10 hertz beat as James releases the string. Calculate the velocity of the buzzer at the point of release. Okay, so when it gets to A, basically he throws it towards Sabina, which means it's approaching. So we need to figure out the approach speed. To do that, we're first going to figure out what the frequency must be from the beats, the observed frequency, and then we're going to rearrange and find Vs. Okay, so F beats is equal to F1 minus F2. So in this case, we take the higher minus the lower. The higher is the shifted one. So that's F dash minus 512 is equal to 10. So therefore, F dash is equal to 522. And then we take the equation F dash is equal to F VW over VW minus Vs. And now we can rearrange. So we multiply both sides by VW minus Vs. So we get F dash VW minus Vs is equal to F VW. We divide by F dash. So VW minus Vs is equal to F VW over F dash. And then we can rearrange as follows. So VW minus F VW over F dash must be equal to Vs. And finally, we can put in the numbers here. So 343 minus 512 times 343 over f dash, which was 522, is equal to Vs. So let's do that. So 343 minus 343 times 512 over 522 gives us 6.57. 6.57 meters per second. Okay, so that's a typical Doppler effect question with a little bit of beats mixed in.